we said that an orthogonal set was a set of vectors that were all orthogonal to each other. An orthonormal set is a set of orthogonal unit vectors. So not only are the vectors perpendicular to each other, each one has length 1. In a similar way, we'll say an orthonormal basis is a basis that is an orthonormal set. So it's a basis made up of vectors that all have length 1 and are mutually perpendicular. So we've already seen that this is an orthogonal set, u1, u2, and u3. So if we want to make them orthonormal, we'll just have to divide each one by its magnitude. So the magnitude of u1 is the square root of 1 plus 1 plus 1, that's the square root of 3. And the magnitude of u2 is the square root of 1 plus 4 plus 1, so that's the square root of 6. And the magnitude of u3 is the square root of 1 plus 0 plus 1, so that'd be the square root of 2. So we can make an orthonormal set if we just normalize these. Maybe I'll change their names. v1 will be u1 divided by its length, so that's going to be the vector 1 over root 3, 1 over root 3, 1 over root 3. And v2, I'll just take u2 divided by its length, which was root 6, so that'll be the vector 1 over root 6, negative 2 over root 6, and 1 over root 6. And finally v3, just take each element in v3 and divide by the length. So now we have a set of 3 vectors that are not only mutually orthogonal, but they're all unit vectors. So we have a v1, v2, v3 forms an orthonormal set. So here's a set of vectors. Is this an orthonormal set? They each have length 1, but they're not perpendicular to each other, right? So no, they're unit vectors, but not orthogonal. Okay, what about this set of vectors? Is this an orthonormal set? Well, let's see. First, let's check the length. Well, I guess we should check the dot products, right? If we dot the first with the second, we're going to have 1 over the square root of 36 plus 0 minus 1 over the square root of 36. So the first two are perpendicular, or they're orthogonal. And here we're going to have negative 2 over 3 root 18 plus 4 over 3 root 18 would be 2 over 3 root 18, and then minus 2 over 3 root 18. So the first and the last are orthogonal. What about the second and the third? Yeah, it looks like it, because we'd have negative 2 over 3 root 2, and this would be positive 2 over 3 root 2. So it's definitely a set of orthogonal vectors. Now we just need to check and see if they're orthonormal. So do they all have length 1? So checking this first one, we would if we squared this, we'd get 1 over 18 plus 16 over 18 plus 1 over 18. That would be 18 over 18, which is 1, and the square root of 1 is 1. So this one is a unit vector. If we square this, we get 1/2 plus 0 plus 1/2. So 1/2 and 1/2 is 1, and the square root of 1 is 1. So this is a unit vector. And this last one, if we square this, we get 4/9. Plus 1/9 would be 5/9, plus another 4/9 would be a total of 9/9. That's 1, so the square root of 1 is 1. So yes, this is a set of orthonormal vectors. We have this theorem. If you have a matrix that has orthonormal columns, then its transpose is actually its inverse. Or if a matrice's transpose is inverse, then you know that it has orthonormal columns. So that all rests on the fact that U transpose U, the rows of U transpose would be the columns of U. So when you're doing this matrix multiplication, you remember we multiply row by column. So these entries, the first entry is going to be U1 transpose U1, U1 transpose U2, and so on, right? It's basically just be in the ijth position, we'd have the uth row with the jth columns. So let's assume first that this matrix is equal to the identity. Well, remember, U1 transpose U1 or UI transpose UJ in general is going to be the dot product. So if this works out to be if U transpose U turns out to be the identity matrix, then what we know is that the dot product of each each pair on the column, right? Each column with itself, each pair on the diagonal, sorry, each column with itself is 1, because that's the entries on the diagonal. And if you take the dot product of anything off the diagonal, that's a vector with a different vector, and so all of those are going to be 0, and so that proves that the columns are all orthonormal. On the other hand, if we had orthonormal columns, then we would know that all of these products are 1, right? Because the magnitude of each vector is 1, and if you dot a vector with itself, you get its magnitude squared. So we know that these are all 1s, and the ones off the diagonal, since they're orthogonal, all of these dot products would have to be 0, so we'd have the identity matrix. This is kind of a neat property. If the columns of a matrix are all perpendicular and they all sum to 1, then we know that the transpose of the matrix is actually the identity. Okay, so we define, when we say an orthogonal matrix, we mean a matrix. We probably should say orthonormal, but the definition is orthogonal, right? So it's a matrix that has orthonormal columns. Well, the definition of orthogonal matrix is that its transpose is inverse, but because of Theorem 6, we know that that matrix has orthonormal columns. We know that those columns would have to be orthonormal. Okay, so let's do just a couple things with this. Suppose we have a matrix that's n by n, and we want to show that the rows of that matrix form an orthonormal basis for Rn. So certainly the columns form an orthonormal basis. So the question is, what about the rows? Okay, well, let's call this matrix, let's call A actually U transpose. U transpose, its columns are the rows of A. So if I can show its columns are the rows of U. So if I can show that U transpose is an orthonormal matrix, then that would mean that the columns of U transpose, which are the rows of U, are orthogonal vectors. Okay, well, let's see. What if we take A transpose A? Well, that would be, A transpose would be U, and A is U transpose. Okay, but we know that if a matrix has an inverse, well, we know because U is an orthogonal matrix, that U transpose really is U inverse. So that's the identity, but we also, so that's enough to show it then, right? Because that shows that A's inverse is its transpose, and therefore A is an orthogonal matrix. And A is U transpose, so that means that the columns of A are orthogonal, so the rows of the original matrix U are, the columns are orthonormal, so we know that the rows of U are orthonormal as well. One last theorem about orthogonal matrices, in other words, matrices with orthonormal columns. When you apply an orthonormal matrix to a vector, it doesn't change its length. And if you apply it to two vectors, it might rotate those vectors, but it won't stretch them, and it won't change the angle in between them. So we have these statements. U times x is the same length as x. Ux dot uy is the same as x dot y. And ux dot uy is 0 if and only if x dot y is 0. So this is saying that an orthogonal matrix doesn't change a vector's length. Applying an orthogonal matrix to a vector doesn't change its length. The dot product between two vectors stays the same if you transform both of them by applying an orthogonal matrix to them. And if they're originally perpendicular, then after you apply U to them, they'll still be perpendicular. Or if you apply U inverse, they're perpendicular to begin with, then they'll be perpendicular afterward. So each of these statements is based on the idea that if you want to do a dot product, so if you want to take vector A and dot it with vector B, then what you're really doing is A transpose B. So for this first statement, we see that, okay, the magnitude, let's think about it in terms of the squares of the magnitudes, because if those are the same, those will be the same. So the magnitude of ux squared is really ux dot ux, but that would be ux transpose times ux, and ux transpose, the transpose of the product is the reverse product of the transposes, so that's actually x transpose u transpose times ux. But because it's an orthogonal matrix, because the columns are orthonormal, u transpose u has to be the identity. So we get x transpose identity x, or just x transpose x, which is x dotted with x, which is the magnitude of x squared. So the length of a vector before you multiply it by u and after you multiply it by an orthogonal matrix is the same. And we can go through a similar process here, right? Because ux dot uy is going to be ux transpose times uy, but the transpose of the product is the reverse product of the transposes, so ux, the whole thing transpose, is x transpose u transpose times uy. Again, we've got an orthogonal matrix, so the columns are orthonormal, so that's going to, u transpose u will be the identity, so this will just be x transpose iy, which will just be, since that's the identity matrix, just x transpose y, which is x dot y. Okay, and I guess I should have just proven that one first, because the rest of these things all follow from that. So from this one, so if that dot product happens to be 0, then this dot product will also be 0, or if this dot product is 0, that will be 0.